Welcome to lecture 2. So in this lecture let's discuss the topic on current and resistance. So after you complete this section you should be able to describe the basic properties of electrical current, and you should be able to solve problems relating to current, charge and time, and you should be able to distinguish between different drift speed of a charge and the average speed of the charge carrier between collisions. And third, you should be able to calculate the resistance, current and the potential difference by using the definition of resistance. So you should also be able to distinguish ohmic, non-ohmic materials and learn what factors affect the resistance of these materials. So let's start with current. So electrical current is the rate at which electrical charge passes through a given area. For example, let's say if this is a given area and there are multiple charges that are trying to pass through it. So the amount of charges per unit time is called current. So the amount of charge that passes through a given area over the time interval is defined as current. So we write it as I equal to del Q by del T. So what is the difference between the two currents? There are two types of things that we generally see. One is electrical conventional current and electron current. Conventional current is the flow of positive charges. Electron current is the flow of electrons. Electron current represents the flow of electrons, and conventional current is the representation of the flow of positive charges. So however the positive charge is flowing is what we consider as conventional current. So if you consider a circuit, if you consider this as a conductor, and let's say that in this conductor there is electrons that are flowing in this direction. So the direction of electron current is the forward direction here, because the direction in which electrons travel is the electron current, and opposite to that is conventional current. So conventional current and electron current are opposite to each other, and one will flow in the other direction to the other. So with this brings up the question of drift velocity. So drift velocity is the net velocity of a charge carrier in an electric field. So moving in an electric field. So an electron does not have a set path that it can go through. It has to undergo multiple collisions. In this path, it takes in a mean velocity. That mean velocity is what we call as drift speed. And always the electric field is opposite to that of the negative charge. Remember that the arrow here represents the flow of positive charges. So that's the reason why it's in the opposite direction of the electron flow. So these drift speeds are generally relatively small because there are many collisions that occur when an electron moves through a conductor. So there are many things that can occur when an electron flows through a conductor. So how do you calculate drift velocity? So the formula for drift velocity, the formula for current I is given as NQ Vd times A. So where N here represents the electron density, Q here represents the charge of the charge carrier. For example, if it's considered as an electron, so we will consider the charge of an electron here. So we are talking about each individual electron here. So Q here, let me write it simpler so that we don't need to confuse every time. So flow is the charge of electron. So which is 1.602 times 10 to the power negative 19 coulomb. So Vd here represents the drift velocity, and A here represents the area of the conductor. So depending on the type of conductor we can consider this part. So there is one other quantity that we generally consider. So we call that the quantity is called current density. So current density J is given as the ratio of current and area. So I by A. I here is NQ VD times A by A. So when A gone, you will get NQ into VD. So this is the formula for current density. Next, let's discuss resistance. So resistance is basically opposition to the motion of electrons inside a conductor. So it is the opposition presented to the electrical current by a material or a device. So the SI unit is ohm and it's equal to 1 volt per ampere. So 1 ohm is equal to 1 volt by ampere. So we can write resistance R as delta V by I. So delta V by I is potential difference by current. So what is resistance to what are properties? So for many materials, resistance is constant over a range of potential differences, and these materials are generally called ohmic materials. In ohmic materials, the voltage is proportional to the current. So the proportionality difference is a linear relationship. So it is a linear relationship. If you have materials that do not obey Ohm's law, we call that non-ohmic materials. Non-ohmic materials have delta V here does not be proportional to IE. So these are called non-linear relationships. So we call them non-linear relationships. So resistance depends on the length, the cross-sectional area, temperature, and the material. So these are some of the factors that resistance does depend on. So with that in, what is Ohm's law first? So before we go into anything else, let's discuss what is actually Ohm's law. So Ohm's law says that at constant temperature, the current passing through a conductor is proportional to the voltage maintained across the conductor. So this is Ohm's law. So it basically states that when delta V is proportional to I, provided T is constant. The reason T is constant we'll discuss when we go through resistance. So what are factors that affect resistance? Number 1 is length. Number 2 is cross-sectional area. Number 3 is material, and number 4 is temperature. So let's discuss the first 3 relationships. So resistance is proportional to the length. So as the length increases, resistance will increase. Resistance is inversely proportional to the area. So a smaller wire will have lesser resistance, a longer wire will have longer resistance. Smaller wire in terms of the cross-sectional area will have higher resistance, and the larger circumference conductors will have lesser resistance. So here resistance will be low, here resistance will be high. Here resistance will be high, here resistance will be low. So this is the idea behind the first two. Combining both, we get R is proportional to L by A. When you remove proportionality, we get a constant called rho times L by A. Rho here is called as the resistivity of a material. So rho is called the resistivity of a material. So R here, resistance is a phenomenon, but resistivity is the property of a material. Let's call it the mechanical property of a material. Sorry, not mechanical, electrical property of a material. This is a property of the material. Our resistance is the phenomenon that occurs in conductors when current passes through them. So resistors are the devices that we use to control the amount of current that you pass through a conductor. Best example of thinking about it is to think about your electrical heaters. Those are examples of Your kettles are also examples of heaters. They use resistance to produce heat. So salt water and perspiration lower the body's resistance, because those two are the materials that control the amount of current, that is that control the amount of heat that is generated inside your body. So we use potentiometers. These are devices that have variable resistance, which means that you can change resistance. So you can change resistance as desired. So we can change resistance as desired. So use the principles that we have now. So let me do the first problem so that you can do the rest. So what is given in the first problem? So what do we have here? In the current in a wire, so if the current in a wire of a CD player is 5 milliamperes, how long would it take for 2 coulomb of charge to pass through a cross-sectional area of this wire? So they have given us the current I, which is 5 milliamperes. Convert it into amperes, you get 5 times 10 to the power negative 3 amps. The charge Q, del Q, is given as 2 coulomb. So they are asking you for delta T. So we know the formula for I is delta Q over delta T. So if you rearrange the formula for delta T, suppose delta T here, I here. So delta T becomes delta Q by I. So delta Q is 2 coulomb, 2.00 by 5 times 10 to the power negative 3. So when you calculate 2 by 5, that value is 0.4 into 10 to the power 3. So that becomes 400 seconds. So delta T here is 400 seconds. This is how you can calculate the answers when you have the problems. So use the same principle now. Pause the video right here and try to solve these problems. So what is given in the problem here? So they are asking you to find the current in the following devices when they are connected across a potential difference of 120 volts. So you have a hot plate of 48 ohm and a microwave oven with a resistance of 20 ohm. So we know the formula for resistance R is delta V by I. Here they have given us the delta V value is 120 volts in problem A and in problem B. In problem A they have given us R, which is 48 ohm, and they are asking us to find I. So rearranging the formula, put R here, I here. So you get I equals delta V by R. So delta V here is 120 by R is 48. So when you calculate 120 over 48, that gives you 2.5 amperes. In the same principle, use the second one has 20 ohms and they are asking you to find I. So I again becomes delta V by R. Delta V is 120 by 20. So that gives you a value of 6 amperes. So through the hot plate, the amount of current that's passing through is 2.5 amps. And for the microwave oven, it's using 6 amps. So the larger the device, the larger the amount of current that it ends up using. So that's the basic principle behind the topics of the idea behind current and current here. So use the same principle and we are done with problem 3 here. So try to do the other problems. So pause the video right here and try to solve the other problems. Next, let's come to the next section, electrical power. So after you complete this lecture, you should be able to differentiate between direct current and alternating current. You should be able to relate electrical power to the rate at which electrical energy is converted to other forms of energy. And number 3, you should be able to calculate the electrical power and the cost of running electrical appliances. So this is the 4 parts. So let's start with number 1. What are sources and the types of current that we end up getting? Batteries and generators are the ones that generally supply energy to charge carriers. So current can be direct or alternating. What is the difference here? In direct current, charge will move only in one single direction. In alternating current, the direction of the charge movement is continuously altering. which means that it's always going to change from positive to negative and positive to negative. Here it's going to be constant, so there is no change in the direction of the charge. Here it's always alternating between positive and negative, so that's why the name alternating current. So electrical power is the rate of conversion of electrical energy. So we can write the formula as P equals to delta V times I, current times the potential difference. So let's start with the first formula, how energy transfer occurs. Most common energy transfer of power utilization is generally done using a resistor. When you take a look at resistors use power, and that power can be written as I times delta V, but the velocity, potential difference is generally the one that's not known. So we know that delta V can be written as IR. So in place of delta V, if you write IR, you get I square R. In place of I, if you write delta V by R, we get delta V square by R. So this is the formula. These are different versions of the same formula depending on what variables you have in the question. So electrical companies in general measure energy based on kilowatt hour. So whenever you see 1 unit of power, that basically means that if the electrical bill says that you have utilized 280 units, so each unit represents 1 kilowatt hour. Remember the difference here, watt here is the unit of power. But when you put hour next to it, watt hour is the unit of energy. So this is a common misconception between the two units. So just that's because they look the same, so they are not of the same quantity as well. So 1 unit represents 1 kilowatt hour. Electrical energy is transferred at high potential difference to minimize energy loss. So electrical energy is transferred at very high potential differences to minimize the energy loss. So relating to kilowatt hours, this is the, if you use 471, so in the electric bill if you see 471 kilowatt hours, that is the amount of energy that you have utilized throughout the entire month. So pause the video right here and try to solve these problems. So let me show you the first problem here. So you have a 1050 watt electrical toaster operating on a house circuit of 120 volts. What is the resistance of the wire that makes up the heating element of the toaster? So we know the formula here. They have given us power and they have given us the voltage. We need to find the resistance. We know the formula is P equals. Remember that here the relationship between delta V and R. So here we want to find R. So R becomes delta V square by P. So delta V here is 120 square by P is 1050. So 120 square divided by 1050 becomes 13.714 watt. So 13.714, sorry, ohm. This is the unit for resistance that we are calculating. So that becomes ohm. So this is how we generally calculate. So this is how we generally calculate the power based on the values that we have. So use the same principle now. Pause the video right here and try to solve these problems. So with this, we end our lecture on electrical energy and current. So I'll see you guys again in the next lecture.